All right, good morning. Homework 1 is due tonight, and I made a submission box for it, so please submit that after class. Does anyone have any questions on Homework 1, now that you've probably spent more time thinking about it this weekend? Yeah, any questions? Anything? We'll spend maybe 10 minutes going over Homework 1 right now, so any questions? Yes?
Can you go over 3C?
3C. I think we kind of already went over this, but okay, so with this question, what is the first thing that we do? Yeah.
Write out the first inputs and map like what gates are activated and what outputs are being left.
Yeah, definitely. So first you look at, this first set of inputs, which is 0, 1, 1, and then you propagate it through, and that's where I've highlighted all these red numbers. So we say, before time equals 0, then we've entered this like steady state where now the outputs are 0 and 0. Then after that, then at time equals 0, then we enter these new inputs and see what happens, and just kind of see how everything propagates through. Yeah, I have spent quite a bit of time on this question, so I don't want to go over this one again, unless like a lot of people like really want me to like just completely lost on it still. Okay, yeah, sure. Are there any other questions? Did feel like it kind of made sense? Yeah.
I guess for this example specifically.
Yeah.
Let's say like the AND gate, the XOR gate, and the NOT gate are active.
Okay.
Can you count the delay of all of those gates even if the AND gate doesn't change? Or would you only count the delay of the and the XOR gates that would affect Y0?
Yeah, so the question was, if all three of these gates are active, does that mean that the delay is the sum of these three delays? And the answer is that it depends on whether it's switching, and it depends on what is propagating through. So if they're all active, but an input comes that doesn't change the behavior, it doesn't change like the current output of one of these gates, then we don't consider it to have any propagation delay. So like through this AND gate, like if we had like a 0 as one of the inputs and then a 1 on the other input, then like if we change the other input to a 0, then we would say that this AND gate would have 0 propagation delay, because like changing from an output of 0 to an output of 0, we just say like takes 0 time. Yeah. Does that answer the question?
I guess we're just asking like, so let's say the three of them switch.
Okay.
Would you count the delay in the NOT gate if the only output that's changing is Y0?
I mean, if Y0 changes, then yes, there's going to be, that will change the input into this NOT gate, and then it'll cause a new output to be created after 1 nanosecond. So that will, like, the NOT gate will add to the delay if Y0 changes. Yeah. Yeah.
Kind of adding on to that. So if the NOT changes it, but then it doesn't affect the upper AND at all,
Sure.
Is it still counting?
Sure. So you would not count this delay. Yeah, if this AND gate was like locked, if it was like set to 0 by this like A right here, maybe at time equals 0, like now A switches to 0, and so at time equals 0, like this NOT gate is locked in place. It's locked at a 0. It doesn't matter at all the delay through this NOT gate, because this NOT gate is just feeding into this AND gate. So there's no. We would say that there's no like delay that's created by this NOT gate. Yeah.
Sorry, just to add on to that, I was wondering if you could just quickly explain what's happening at the very end part of that AND gate. Like, I think you added a couple more delays to it, and I was just wondering if you could go over that.
You're talking about the example that I went over last time? All these like numbers?
But like more specific towards the end of that. Because I think...
Oh, sure. Yeah. So I guess the point of this was that the AND gate was like in steady state, it was fed in an input that should create a 0. So it was fed in 0 and 1. So this should create a 0 on this end. But then what happens is when it switches to the input of 0, 1 now. But after switching to 0, 1, like we would expect that it would just stay 0, 0, but we actually get this little glitch of when for just a little bit, there's some overlap of when this 1, 1 takes place. And because of this 1, 1, that actually means that, yeah, now we have a glitch where it's 1 for like a little period of time. And so it takes, we would say that the delay is actually dependent on this hazard. It's not, like you would think maybe first off you would think that the delay would be 0 because it's switching from 0 to 0, but actually, yeah, there's this little glitch, so there's a little bit extra delay. Yeah. Okay. Yeah.
Is 14 nanoseconds the correct answer for C, or do we?
No, I just made this number up. So I said if we had the condition at time equals 0 that it switches from 0 to 1, and we had the condition that it swapped from 1 to 0 at time equals 11, which I don't know if that will actually even happen. So if you have this condition, then yes, then the correct answer would be 14. So if you had these inputs, then the correct answer would be 14. Yeah.
So for D, should we swap the second set of outputs for 0, 1?
Should we swap the second?
How can that less than is 1, 0, and 1?
Say it again.
The second set of outputs where you put 0, 1 right there.
You're talking about like, yeah, this part that I like whited out.
Yeah, I'm hoping to change that.
Yeah. There's a slight typo. The actual output is 0, 1.
Okay.
Yeah. Okay. Okay. Any other questions on any other part? Yeah. Lookup tables. That makes sense. I guess we did go over most of these already. Yeah. Any other questions? Yeah. Yeah.
Question about question 9C.
Yeah.
I was wondering right there, would it be A, B, and would it just be 0 for C, or would we just not describe any of that unknown?
Yeah, so it's completely up to you. If you assigned 0 and 0 for C and D, then that would just mean that you would need to fill your table accordingly. So yeah, maybe let's go over this part one more time, just because, yeah, it is a little bit confusing. So let's say that this is our table right here. And so how many elements will our lookup table have? Yeah, it'll be 16, right, because there's 4 bits, so the largest address that this can have would be like 1111. Okay, smallest is 0000. Okay. Yeah, and if we hardwired zeros right here, then what, like if we were trying to fill this element in our lookup table, what should we probably put as our output? If we're like asked like in our table, like if we ever receive 1111, what should our output be?
Error. 0.
Yeah. Well, is it ever going to happen? In this case? So we're feeding 0 and 0. We're hardwiring that into C and D. So is this case even going to happen? No, it's not going to happen. So it doesn't matter what we put here. And we would call this a don't care. So we could put like an X here if we wanted. Or we could put 1, we could put 0. We could put whatever we want because we don't care. Yeah. What is an address that we do care about? Shout out. Yeah.
0, 1.
What is it?
0, 1, 0, 0.
Sure. Okay. 0, 1, 0, 0. So C and D are 0, 0, and looks like okay. So that matches. That is a possibility that could happen. Okay. Sure. And then what would the output of this be? Yeah, it'd be 1. Yeah. What about this one? 0, 0, 0, 0. Is this possible? Do we care about what is set here? Yeah. Okay. What would the output be? 0, yeah. Okay. Yeah, so this table is kind of the most important thing. So first you assign like kind of the inputs to your lookup table, and then after that, then you fill out this table according what will create the correct function. Yeah.
We use X's for C and D, or would that not be okay?
Sure, yeah, and so if we had x's for here, how would our table change?
It'd just be 4 for other ones.
Yeah, I don't know. So if we didn't care what C and D are, meaning like C could be 0, C could be 1, D could be 0, D could be 1, then what should our output be for 1, 1, 1, 1? Does it matter? Yeah, it does matter. Because we could just, we didn't really care. We said we didn't care. So our tool could have chosen to assign 1 and 1 here to C and D. So if it chose 1 and 1, then all of a sudden, yeah, we care what this output is. Yeah.
Would it make a difference if A and B was the last two bits of the lookup table and the address was zeroed out?
Yeah, sure. So we could totally put like A and B here. And yeah, put zeros here. Yeah, and that would now change things slightly, because now these two like places would correspond with the inputs, as opposed to before it was these two spots would correspond to our inputs. Yeah. Okay. All right. Cool. Hopefully that's enough. Yeah. Question.
I was going to ask a question about 9B.
Sure. Yeah.
You said we can't use inverters.
Yes.
Can you go over a way you would implement it?
Yeah, so we can use a mux. So if we have a mux, is there a way that we can turn a mux into an inverter? You may use multiple muxes, yeah, in general. How do you create an inverter from a mux? So if we have the inputs 0, 1, what should go up here? 1, what should go down here? 0, what should go right here? Input, and what's here? Yeah, okay, cool. Okay, cool. I'm going to move on. So on Friday, we went over a new circuit element. What was this circuit element called? Flip-flop, yeah. Okay. What is a flip-flop? What does it do? Yeah, anyone give a quick explanation of a flip-flop? No? Yeah.
It stores bits.
Sure, yep, stores bits, so it's a memory device that stores bits. How do you update the value that's currently being stored in the flip-flop?
For a positive and negative edge on the clock.
So in last class, I only went over positive edge, clocks. Yeah, exactly. So when you receive a clock edge, a positive clock edge, meaning it switches from 0 to 1, so at the instantaneous moment that your clock signal switches from 0 to 1, then that is when your input on the D side, your input is now transferred over to your output. So that is a flip-flop? Yes. Okay. And we went over some kind of basic circuits. So every cycle would divide whatever was currently stored in the flip-flop, and it would divide it by 2, divided by 2, divided by 2. Yeah, so we can see, first it stored 32, then 16, then 8, then 4. Just with this circuit, where we just kind of looped it back into itself. Yeah. And then we went over some examples with just OR gates, AND gates plugged into it, saw how the waveform reacted, did it a couple times, saw how it reacted with unknown values, and yeah, I guess that was it. So this class, we're going to go over more ways you can utilize flip-flops. I'm also going to talk about your next lab. So your next lab, if you notice, your next lab is not due this Friday. That is because this is your first hard lab, meaning it's going to take a lot of time. It's going to take the full 2 weeks. Last quarter, at least, like a lot of people did not finish and had to come in late. And so please, like, it's like, oh, week off. It's like, no, absolutely not. Like, go in tomorrow, really try to work through the lab as much as you can. You may not, there may be just weird bugs that you encounter. So please go into the lab tomorrow and work on it. So I'm going to go over the lab a little bit today. First I wanted to just go over a little bit more with flip-flops. So, so if you remember, so at the very end of class, I mentioned an extra input on a flip-flop called a reset. Do you remember what the reset does? Yeah.
It resets the bit that's stored.
Exactly, yeah. So most importantly is it turns it to a known value. Because like when you initially plug in your circuit, and this goes for everything, so even on your phone, everything, there needs to be some sort of signal that tells all the flip-flops what their initial values should be. And this reset can either tell the flip-flop to reset to a 1 or can tell it to reset to a 0, depending on what type of flip-flop it is. So when you create flip-flops, you can determine at that time whether you want it to reset to a 0 or a 1. In most examples, it's going to be reset to 0, though. Okay, yeah, so we have reset. And so let's go over, so let's go over this quick example with a reset. So another important thing, so with resets, there's a few different types of resets. So I'm going to go over just one right now, where we have an active low synchronous reset. So synchronous meaning it will update, like the Q value will update according to the clock. So if the reset goes active, it must wait until the next clock cycle to become reset. And then also active low, and there's this little inverter sign right there. This is a very common type of reset where if the value is low, that is when the reset is enabled. And when reset goes high, that is when the reset is disabled. And actually, most commonly, the way you denote an active low reset is by putting a little _n next to the name. So let me just do that really quick, like this. Yes. Okay. Try to solve this right now. Spend a minute looking at this, and then I will go over the correct usage of a reset. But yeah, see if you can figure it out just from this prompt. So starting out, so Q0 is unknown, but if we look at the first pause edge, then now we have whatever, A is set to 1. So if A is set to 1, if we ignore everything else, if A is set to 1, then A will go through this OR gate and will be fed into this flip-flop. So what would we imagine the next value would be if we ignore everything else? Say it. 1, yeah, so if A is 1, right, it'll be, the 1 will go into this OR gate, so then we would imagine that on the next cycle, it would be set to 1. However, is reset active? What was that? Yeah. Yes, it is, because it is low. Remember, this is an active low reset, so it is active. So that means that it will overwrite, no matter what, it'll overwrite whatever is being passed into D, and instead, let's say it is reset to 0. So that means at this pause edge, cool, so we get reset to 0. Okay. Next clock cycle. So our reset, is our reset active? No. Goes high, so it is deactivated. A is now 0, so that doesn't tell us anything. But now we look at Q0. Q0 is 0, so what will be passed into D? 1, yeah, because there's this little NOT gate right there. If you could see that. Yeah, so therefore, on the next clock cycle, Q0 will be what? 1, yeah. Yeah, because of this NOT gate right there. Okay, cool. So then this continues. Now we have A goes to 1. So just very clearly, we can tell that for this whole period right here, we will have Q0 at 1. Make sense? Yeah, because A is 1 this whole time. So let me further this. Okay, and then one more. Okay, and now reset goes low. So on the next clock cycle, what will the output be? The next output will be 1. Why is it 1? Yeah. Question? Oh, starting here?
Why is Q0 1 after 4 pricing
At the
for clock, right? So the clock has 4 pricing events.
uh-huh.
Why is Q so after 4 pricing events the clock?
Oh, fourth. Okay. So 1, 2, 3, 4.
And why is Q0 1?
Oh, 1 on the next one? Oh, you know what?
Because it should be looking at
You know, I think you're totally right.
4A. So if A is 0.
Yeah, you're totally right. Yeah, thank you. I'll fix that in a second. Yeah. Okay. Do we have an explanation of why this is 1? Anyone? Does anyone? Yeah.
A was 1 and also Q0 was 0, so it would be non-zero.
Yeah, exactly. But most importantly, this reset right here doesn't like become passed into D, doesn't become like passed in until the next like clock cycle. So this reset, even though it goes low, it actually wasn't activated yet. So yeah, so it stays high. But on this next clock cycle, now reset will become activated, and then that is when now yeah, our output is 0. Someone mentioned actually, so right here, I made a small mistake. So notice that on the previous clock cycle, A was 0, and on the previous clock cycle, Q was 1. So therefore, because we have both those things, we actually have this little dip to 0 right there. Yeah, so my mistake. Hopefully this makes sense. Okay. This is a very common confusion for people, is the idea of like when something happens on a pause edge, the idea that you need to sample before the pause edge and not sample like directly after it. So yeah, just be careful of that. Okay. I want to do the exact same example, except instead of a synchronous reset, now I want to do an asynchronous reset. So let me write that out. So this is a synchronous reset, and now let's do an async. Okay. So most of it is going to stay the same. So, so this section all right here, we actually know what this value is going to be. Because asynchronously, any time that reset goes active, so just for the entire duration that reset goes active, we know for a fact that, that the output must be 0. So actually, instead of it being unknown, instead we know what this value is. And what is this value? Yeah, this is all 0. Because this reset is set. And similarly, right here, so this reset goes low. So therefore, right here, what will this value be? Yeah, also 0. And you know what, I'm going to do it in a different color. Yeah. Okay, so that is asynchronous resets. We've gone over, yeah, active low. If you can imagine that there's also active high resets. So sometimes you will see that and it will be clearly denoted in your question. Yeah, and most likely the circuit diagram in an active low reset, you'll have this bubble. If it is an active high reset, you will not have this bubble. So yeah, there's lots of different permutations of how to create that. Okay, makes sense? That's good. Yeah.
Why does the output dip again on the fourth clock cycle?
Oh, right here?
Or the little before?
Oh, right here. Yeah. It is because on this previous clock cycle right here, so on this previous like time step, we can see that A is 0, and we can see that Q0 is 1. So if we look at this, so Q0 being 1 is going to be passed in as 0. A is also passed in as 0, so we have 0 or 0. So that means that, yeah, we have 0 right here. And our reset is, so it doesn't matter what our reset is, because, yeah, we are being reset to 0 anyways. Yeah, okay. Cool, okay, that is all the types of resets. Yeah.
Sorry, what changed between the asynchronous and the synchronous examples?
Yeah, so the highlighted part in blue is what changed?
Or I mean, what conditions changed to make Q change?
So asynchronous, meaning it does not care about the clock, and instead this reset just, no matter what, it will like destroy whatever value is currently being stored inside of Q, and it will override it with 0 immediately, regardless of the clock.
So you just pretend the clock doesn't exist?
Exactly. Anytime the asynchronous reset is activated, then you ignore the clock and you just reset the flip-flop directly. Yeah, okay. It is beyond the scope of this class to determine like which one is better for which situation. It has to do with if your chip has like multiple clocks and yeah, you're trying to like reset things across clock domains. So I'll just kind of say that if you want to like look into it, it's called clock domain crossing, and you can look at how asynchronous resets are useful in that case. However, we're not going to talk about it in this class. The most that you'll get is I'll say, oh, imagine that you have a circuit with an asynchronous reset. I'll say, imagine you have a circuit with a synchronous reset. So everything that you will do in the labs must be a synchronous reset. Okay. I want to go over one quick circuit, and then I'm going to implement it in Verilog to show you actually how you create a flip-flop in Verilog. Okay. So, yes, good. So I want to make a 2-bit counter that behaves like this. So we can see Y0, every other cycle, it oscillates up 1, similar to, yeah, if you just think of like how an adder should work, right? So we have, it's counting from whatever, 0, 1 to 1, 1, and then 0, 0, and then 1, 0, and then 0, 1. So it's adding up, it's counting up. So let's think of how we can make a circuit that could do this. Okay. Take 1 minute, see if you can draw out the circuit, and then we will go over it. Okay. How many flip-flops are we going to have? 2. Yeah, very clear to tell because we have 2 outputs. Okay, let's not use a bus right now. Let's just use straight flip-flops, and let's also ignore reset, even though a real implementation should definitely use a reset. Okay, so we have D and Q, and maybe we should also have maybe a. Can we get it done with a single full adder, or do we need more than that? What do people do? Anyone want to share? How do they use like an adder? I'm assuming you used an adder circuit, right, to make this? Yeah. Yeah, so I think you can just do it with, yeah, a single full adder. So I'll bring these over. So what does a full adder take in? How many inputs does a full adder have? 3. Yeah, full adder has 3 inputs. Okay. And actually, do we need more than that? It looks like actually, yeah, we will need a couple ladders, right? I think we'll need 2 full ladders. Maybe we'll connect that. Okay. Is this what people did? Or is not what people did? Okay. So assume that maybe this full ladder, so this has some sort of output. Maybe this is going to be like going to produce our lower bit. This is going to produce our upper bit. So we could probably just pass this directly into these Ds. Okay. And then after that, then now we have this. So these denote like Y0, Y1. Okay. How should we pass these back in? Anyone want to walk me through it? Okay. I'll get you started even more. So if you take this now, pass it in to maybe like this guy, and then take this, pass this into this guy. Okay, so now we just have these 3 inputs left that are not set. So if we just assign this all to 0, so let's do that. So if we assign it to all 0, what's going to happen is we have this flip-flop that is outputting into this full ladder, and then this input is probably just like passing directly through, and then it's set to Y0 again, right? What's going to happen is it's just like a circular loop where nothing's going to update, yeah? Similar with this, Y1, if Y1 is being fed into this full adder, there's never going to be a carry that's generated because, yeah, like it's the maximum value that this will just be 1, so there's no carry, right? So in both this cases, it's just going to be like fed into this adder, and nothing's going to update. But that's not what we want. We want it to increment by 1 every time. So what do we need to change on this in order to get it to increment by 1 every cycle? Okay, go and tell the person next to you. Hopefully you should be screaming it in your head now. So go and tell the person next to you. What do you change on this? Question or answer? Yeah, I drew it a little weird. This is 1 input. You know, here, let me draw it more consistently. So this is another carry input. Yeah. There we go. Yeah, so now you can see, so there's 1 carry input, and then 2 regular inputs, and then 1 carry output, and then 1 sum output. Yeah. So I just clarified the diagram. Nothing has changed. Okay. Yeah, okay. What of these 3 inputs should change? Yeah.
The 0 on the top full adder is the second input.
Sure.
Not the carry.
Yeah, well, I don't think it matters. It could be either one of these. Yeah. And what should it change to?
A 1.
Sure, yeah, so 1. So what that is going to create is now we have Y0, so the least significant bit, is now going to be added with 1. And let's say Y0 was 0. Well, then now it's going to be 1, and it's going to have incremented, pass in here, all happy. But if this is a 1, so if we have now 1 plus 1, then now this will be a 0, but it will propagate the carry out to this next full adder. And this next full adder will add the 1, and it will add it with whatever was stored in the flip-flop. So this circuit, and I can redraw my wires to look a little bit better, but this circuit right here is exactly what I was looking for, and it will exactly implement this output. Yeah. And actually, did we did we need full adders for these? No, yeah, it looks like actually for both of them, we probably could have just had a half adder because we plug in a 0 for one of the inputs. So, anyways, yeah, okay, good. I'm gonna move on to this next example. Okay, so a 4-bit counter. So, you know, yeah, this 2-bit counter, it was a lot of fun drawing out the full adders and the flip-flops. Let's now use buses. And instead of this like chain of full adders, now maybe you can use like an n-bit adder. Okay, spend 1 minute now designing this circuit. So use buses, make it a little bit cleaner, and then maybe try to imagine what would go inside of each of these boxes. Each of these boxes should store the value of a bus. So, okay, go and spend 1 minute thinking about this, hopefully drawing out a solution. All right, so, yeah, that's fine. Okay, so 4-bit counter. So how many flip-flops should we imagine for a 4-bit counter? 4, yep. But let's instead just draw one single circuit, one cell, D, Q, clock input, and yes, maybe this is now a 4-bit output. What will now be the input to D? How many bits is this? Yeah, also 4. Okay, good. And now we can probably also create just an adder circuit. So what should an adder circuit take in as inputs? Yeah, so probably Q. And then, so if we're adding in Q, then what should the other input be? If we want to like increment up every time? Yeah. 1. Yeah, sure. So now we're just adding 1 to this output, and then we take this output, and then we can pass this into our D input on our flip-flop. Yeah, and how many bits will this produce? Will this use? Yeah, so let's say it's 4. And so that means that there will be overflow because we're taking a 4-bit value, and if we add something to a 4-bit value, then we would need at least 5 bits to preserve like all precision. So there will be overflow that happens, but that's fine. Okay, great. So now we have drawn our first ever counter circuit. You will all be sick of counters by the end of this class because counters like control the entire world. Like in your phone, there's probably like, I don't know, 1,000 counters just all around it. Okay, and let's say that Q stores 7. No, yes. Okay. What is 7 in binary?
111.
Yeah, 111. Okay. So what will, now back to decimal. Okay. What should D be now if the key was 7? 8, yeah. Okay, cool. And then on the next clock cycle, D is moved into Q, so now we have 8. And then what will D be? 9, yep, so we just increment by 1 every time. And then let's say we, keep going, until finally, now we are storing the value. What's the maximum value we can store in this counter? Yeah, it's 15. Yeah. Oops. Okay, so if we're now storing 15, then what will the next value of D be? What is it? 0, yeah, right. So now D will be 0, and on the next clock cycle, what will happen? This will be 0, yep, and then D will be what? 1. Yeah, 1. Yeah. So when you open up GTK wave, remember the waveform viewer, kind of like an oscilloscope like equivalent, you can actually see, like when you will, in your lab, you will have to implement a counter, and you will actually see like the numbers increment, and it'll follow this exact pattern of, yeah, like Q keeps going up by 1, and then D will be like 1 step ahead. Okay, I want to switch to some Verilog right now to show you the syntax for creating flip-flops. Okay. So here, circuit, so I have clock input, A and B, okay? And I'm just gonna tell you, so the syntax is brand new. So you have to create a new block called always FF. FF meaning, what do we imagine FF stands for? Flip-flop, yep, always flip-flop, okay? And then you say at pause edge, and then you specify what the name of your clock is. So in this module, the name is clock, and then after that, you do begin and end. And begin and end are effectively just like curly braces if you're used to like C-style languages. It's effectively this, except in Verilog, for some reason, they really wanted to have it be like extra verbose, so now it's begin and end. Yeah, kind of interesting. And then inside of this, what you will say is, actually first before this, I'm now going to create the flip-flop ports. So let's call it data, and anytime you create a flip-flop port, you must always have an underscore D input for the D side of your flip-flop, and an underscore Q side for the Q side of your input, for the Q side of your flip-flop. And then inside your always flip-flop, you will assign your output to the input using this operator right here. So this was just like a dump of syntax. So it might be good to either write this down or take a picture. This is how you create flip-flops in Verilog. Okay, and if I run this, oh no, it's because I didn't assign inputs. So now what I should do is assign probably data D. What should data D probably be equal to if we look at these? Yeah, A, like that. And then what should B be equal to? Yeah, data Q. Yeah, so here is our flip-flop cell. So Digital JS Online is used to interpreting flip-flops and has created this flip-flop for us. You can see clock is oscillating for us. And I can go and I can change this, and now you can see B is outputted. But if I now change it, but the clock hasn't changed, see that how I'm changing it? It's still storing 0. But now if I hold it for longer, then now B will change to 1. So this is the visual for flip-flop. Okay. Of course, there's something very important that we're missing from this example. What are we missing? Reset, exactly, yeah. So for reset, we will need to have another input into our module. So we'll call this reset. And let's make it an active low reset. So how do we denote an active low reset in the name? What do we do? Underscore N, yes. Thank you for remembering. Okay, another thing, there is a slight issue on all of these ports. What are we missing from all of these ports? Yeah, underscore I and underscore O. So actually this input should be NI, and this input should be A underscore I, B should be underscore O. Yeah, this NI syntax, that's according to the low risk standard. Low risk is a very active company industry leader in writing good Verilog. They decided that this is how you should name your variables, and everyone has decided to follow along with them. I think I posted in the resources tab. I think I have a link to their style guide, so you can read all about it there. But yeah, so NI, this means active low input. This is just regular input, regular output. So now let's change this. So instead of A, this is AI. Instead of B, this is BO. And then we have pause edge clock. I'm going to keep clock the same because Digital JS Online expects the clock to be named clock instead of clock I for some reason. But I'll just make a quick note. Should be clock I. Okay. And then, okay, so then to actually create the reset, inside of your always FF block, you will create an if statement. So if you would say not reset NI, then begin, and you put this in, except instead of assigning it to data D, you will reset it to whatever the reset value is. So probably 0 in this case. Then after this, then you do else begin end. Yeah. So we will talk more about if statements in a few weeks. You can actually create if statements in Verilog, and it makes sense, and we'll talk about this. But hopefully this block kind of makes sense. It's like we're saying if the reset is activated, meaning like it's like active low, like if not reset NI, so if it's activated, then set data Q to 0. Else, so if reset is not activated, then set data Q to data D. And so now if we hit run, most likely, yes, it'll infer this mux up here, and that's because we need to enable optimizations to see what actually happens. So now we hit run, and there we go. So now we have this S reset with a bar on top. What does S reset mean? What does the S mean? Synchronous, exactly, yeah. What does this bar mean? It means not, yeah, it means active low. There we go. So we've now created a flip-flop with an active low synchronous reset. What if we wanted to make this active high? What would we change? Yeah? Exactly, yeah. We would get rid of this exclamation point, and what else would we do? Yeah, and then we'd have to change the name. Yeah. Is that it? I think that's it. Yeah, hit run. And so now we can see that the bar disappears. So now this is active high. Yep. I'll quickly just show you how to make an asynchronous flip-flop. Please don't do this in the lab, but like maybe it's still good to know in case I ask you a question about it. So in this pause edge clock right here, so this is called the sensitivity list. So inside this, you can specify anything that you want this block to like be run on, you can kind of think of. It's not really being run because it's generating hardware, but what you could say is you could say or pause edge reset. And now if we run this, then yeah, there we go. So now we can see that it is a RST. What does A mean? Asynchronous, yeah. And so let's just see what happens. So if I like set B, so there we go. So B is now set. So immediately, so you can see the clock is whatever, 0, 1, and 0, and then 1, and 0. But if I click reset, it doesn't matter where the clock is, it'll just immediately reset. So now I'm gonna click it, I clicked it, and immediately reset. Yeah, so asynchronous, there we go. Okay. Yeah, please don't do this. I'm going to delete this. Cool. So now it is back to being synchronous, and I'll move it back to an active flow. There we go. Okay. Kind of make sense? Yeah. It's just something that you're going to have to kind of memorize. You're going to be very used to this syntax by the end of the quarter. This is just in Verilog, people at Intel, like when they're creating flip-flops, this is just what they have to write like 100 times a day. So, yeah. I don't know who was first. Yeah, question.
How do you change the frequency of the clock?
So that's a really good question. I'm going to come back to that. Was that other people's questions? I'm going to answer another. Yeah, question.
Does reset always reset it to 0?
So depends on what you set right here. So yeah, so if we wanted, we could actually reset it to 1. And if we hit run, then now if I hold reset, then now we can see.
It's active low.
Oh, my bad. Thank you. Yes, exactly. So yeah, you can see that it's being reset to 1 this whole time. And notice it's active, yes, because it's 0, it's active low. Yeah, so you can reset it to 1. But for the most part, you reset it to 0. And if I don't specify, then I would say just always assume that it resets to 0. So by default, assume it resets to 0. Yeah, another question.
Does a clock always need to be named clock?
For this website, yes. But no, it does not.
So in Verilog, like, how would you tell it to know that it's a clock?
Oh, sure. Right. So clocks should only ever be used. Okay, everyone. Clocks should only ever be used in like this syntax, where you have always flip-flop and then at, and then you put the clock in the sensitivity list. And when you do that, as long as this is the only instance that you're using the signal, then it will know that this is a clock signal. And like Vivado will be able to do all sorts of cool optimizations on the signal to like route it more effectively around the chip. Versus if I now, like later on, I was like, oh, you know what, let's actually set data D to clock. It's like, this would be a really bad idea and would probably destroy your software. Probably wouldn't even know that anything went wrong, because most Verilog tools are really bad at giving warnings and errors. So probably it would be like, oh, great, like I solved your thing. And then what you would actually see is when you pull up your design, you would see that it like optimized away your entire design. And so it actually used like 0 gates or something. Now you're just like sad. Yeah, so there we go. Yeah, so that is the answer, is that you should always just put your clocks inside of your sensitivity list. That is the only time you should ever touch the clock. Yeah. Oh yeah, so there's another question though. So how do you change the frequency of this clock? So in simulation, yes, you can change the frequency of the clock. But this circuit right here is completely agnostic to like frequency. Like all we're doing is we're just creating this circuit, and it doesn't really know what the ports are. And so this website has made this like nice clock, and I guess maybe we can change the frequency of it on this website. But in general, anytime that you create a circuit, it is completely agnostic to the clock speed that it is running at. And honestly, like ideally, your circuit should work at any clock speed. Like it shouldn't work only for like specific clock frequencies. Yeah. Does that make sense? Yeah. Okay. Cool. Okay. I'm actually going to have a quick participation quiz in the last 5 minutes of class, unless there are other quick questions that anyone has. Yeah. Question.
When you say HPCLKI, is there any instance where the clock is an output?
Clock should always be an input unless you have created a module that like creates another clock. And I think actually in later labs you do see clock as an output. Yeah, because you're generating a clock. Yeah. I think so. The question, let me write it out, is in Verilog, how do you denote the input and output of a flop. So if you have in Verilog, if you have an input and an output of a flip-flop, how do you make sure that when people are like skimming through your code, that when they see like a line, they're like, oh, like that is like the input to a flip-flop, or like, oh, this is the output to a flip-flop. How can they just look at the like line of Verilog and they immediately know whether it's an input or an output? Yeah. Okay. Does anyone have an answer to that question? Yeah. Yeah, exactly. Underscore D, underscore Q. What is underscore D? Input. What is underscore Q? Output. Okay. Thank you very much, everyone. Class is on Wednesday next.